So let's continue understanding the synthesis process. Okay. And of course, we're not going into details of algorithms of synthesis process, but so that you get an idea, we'll take certain examples and things which will happen inside the algorithms of the synthesis tool. So the first and foremost which synthesis tool does is convert your basically RTL into a Boolean representation. Okay, so this is, let's say for example, this is basically the same RTL representation represented in picture format, or what is known as Carnot map, or it will basically implement that, convert that into a Boolean table or Boolean equation inside the tool. Okay, so this particular, as you know from your, if you remember your logic design college courses, is known as sum of product terms. Okay, so basically sum is nothing but or, product is nothing but and typically in Verilog these conditions are, these symbols are used for these conditions. So basically whatever RTL you may have written, synthesis tool, let's say, as in it uses multiple algorithms, but let's say it converts that into what is known as sum of product form. Okay, so you write your functional specs, functional specs, write it in HDL. Synthesis tool will automatically convert that into truth tables or Boolean expressions, okay, as sum of products. So what are the typical building blocks of sum of products, right? As in you will have inverters, and basically, for example, let's say you have an assign statement in RTL, assign z equal to a and b. It will become this Boolean condition or equation which synthesis tool will hold in its memory. Or you have assign z a or b, it will become like kind of a plus b expression. Plus stands for or in your synthesis tool. So basically it will convert that into a conditions or equation which is represented by binary trees as sum of product form. Okay, so what synthesis tool can do is it can just do straightforward synthesis. Just I'm taking a hypothetical example that, okay, this is your sum of product form. Okay, so a or b, whatever that condition is, it can implement that logic. Now these are technology independent logic. What someone asked, I think Jayesh asked, is basically a standard gates which are GTech gates, not technology specific. So these are not like different drive strength or different delays as provided by your library files. Right now these are just standard general gates and or gates. Okay, so basically it can, if you think simply, it can convert this Boolean equation into a set of or sum of product equation into gates. For example, this is not of A ANDed with B and C. So this is not of A ANDed with B and C. It can convert this into this gate. Similarly, other conditions also. This, and basically plus then or of all these conditions, and that produces your output. So this is a simple representation. If it synthesis tool is just saying straightforward analysis, you can see the maximum path here has 3 cell delay, one here, one here, one here. Basically this delay, 3 cell delays, assuming 3 cell delays. This is assuming your library will have 3 input AND gates, 3 input OR gates, buffers and inverters. If those are not present, then it will have to modify this circuit accordingly. But if you think of first step, or basically simply thinking, your design or HDL is converted into what is known as Boolean equations, and those Boolean equations are kind of, let's say example, sum of product form, and these are then simply converted into gates, which is the synthesis. Of course it's a complicated process, but we're saying just to understand the principles, we're taking a simple example. Okay, now this is assuming, let's say, what kind of cells which are present in the design. Okay, so let's say here we thought of an example where basically 3 input cells are present, but for example, let's say your library does not have 3 input cell. So then to represent those, synthesis tool will have to use 2 input cells. And let's say you want to implement this condition, but let's say three input cells are not present. Okay, if let's say three input cells are present, so it can just do A, B, and C, and of that, and that produces Z. But let's say if three input cells are not present, then it has to kind of use two input cells to create the same. So depending upon what is present in the library, what is not present in the library, it will use accordingly the cells from your library. Now, this cell and implementing in this cell may have different delays. For example, in the library, this has 0.2 nanosecond delay, and this let's say 0.3 nanosecond delay. But if you implement in this format, it has 0.1, 0.1, for example, and total of 0.2 nanosecond delay. So say which one would synthesis tool use? That will be dependent upon what path it is, how do I, whether synthesis tool is able to meet setup and hold time with this, or it has to use something else. All those optimization synthesis tool has to do. So first is it converts that into a Boolean equation. That Boolean equation is written in sum of product form. Then it chooses the what kind of cells it wants to use. Multiple cells option exists, so it has to figure out which cell to pick, particularly depending upon what a path it is or the area requirement of that. Okay. You can have more building blocks. Sometimes libraries may have more complex cells like NAND cells, NOR cells. Actually, NAND and NOR are most often used, which we'll talk about. Or you can have exclusive or so it has multiple options of representing these equations, and depending upon the situation, what are the constraint, it will choose the best optimal condition for your design, best optimal cells for your design. Okay. As I said, right, typically NAND and NOR are universal cells. Any kind of logic can be implemented just by using NAND gate or NOR gate. Actually, typically the size of design is usually represented in terms of equivalent NAND gate, because most of the logic, if you just use NAND cell, can be implemented. For example, inverter is nothing but if you give both connect A and B input of a cell to the same, it will become an inverter. You can also implement AND, which is basically AND is nothing but NAND and inverter, which is this. So even AND cell can be implemented using NAND gate. No, OR gate can also be implemented using NAND gate. So that's why NAND or NOR cells are called universal building blocks. And typically the size or the amount of cells when a synthesis tool represented is typically written in what you call NAND gate cells. So you may people hearing terms like, okay, my design is let's say 100 equivalent to 100K NAND gates. That is why because NAND gates are universal. NAND and NOR gates, you can implement any functionality using those cells. Okay. So it has created some Boolean representation of the design. Then it will try to optimize that Boolean condition itself. And as you know from Boolean algebra, there are multiple conditions which can exist. So it will do a logic simplification. Okay, logic simplification means it will try to minimize or optimize that Boolean equation. For example, let's say, okay, this is the equation, Boolean equation. Now using some Boolean operations, okay, let's say alpha A and alpha A bar is equal to alpha, right? So alpha A plus alpha A bar means A plus A bar. A plus A bar is 1. So alpha. So it can just be alpha. Now this using these Boolean optimization, logic simplification, this equation can be simplified further. For example, this is A bar BC, this is ABC. So A bar dot BC plus A dot B dot C. If you simplify it, it can become B dot C, A plus A bar, and A OR of A and A bar is 1. So this simply becomes B dot C. Okay. Similarly, this and this will become A dot C and A dot B. Now, so this Boolean equation can be simplified to a simpler format, which will happen inside the synthesis tools. Okay. And this helps, then you can see, right, as an it will help reduce the amount of logic and in term amount of area. So this Boolean minimization, either through algebraic approach or through using Carnot map, whichever method synthesis tool, there are multiple algorithms which exist. It will reduce the Boolean equation which is created. Okay. So what is happening is you give your HDL hardware, it will convert that into what we call Boolean equations. Okay. These Boolean equations will be minimized or optimized. There'll be some additional algorithms which will go on to even minimize it further. Then it will map to standard cells libraries. And these standard cells will then map to your basically it's a 7 nanometer library. So this is the whole step, whole process which happens.